clock's ticking down. You flip the page, and bam, there it is. A massive, high-mark question on electromagnetism just staring right back at you. Your heart rate spikes, right? You know you've studied the textbook, you've done the reading, but in this specific split second, Cambridge Physics 0625 isn't just about what you know in your head, it's about exactly how you phrase it on that dotted line. The marks are literally on the line, and the difference between snagging an A star and slipping down to a B, it almost always comes down to just a handful of carefully chosen words.
So let's imagine a two-student duel. Both students are staring at the exact same question: how do you increase the strength of an electromagnet? I want you to mentally lock in your prediction right now. Which of these two students is going to walk away with full marks, and which one is going to lose a critical grade boundary over a seemingly minor detail? Your choice right here could literally make or break your final grade. Okay, let's dive into this. Student A writes, "You add more power to the magnet and make it bigger." Sounds okay, right? But then student B writes, "You increase the current passing through the coil of wire and ensure it has an iron core." If you pick student B, you are absolutely correct. Spot on. Student A's answer? It's a classic, totally flawed response. It relies on vague everyday language, words like power and bigger. But student B? They hit the precise terminology the examiner is actively hunting for: a current through a coil of wire complete with an iron core. This is exactly where so many students lose marks. They actually understand the concept in their head, but they completely fail to translate it into the exact scientific language required by the mark scheme. And honestly, this is exactly why ordinary revision fails. You can read that textbook 10 times over, but if you aren't writing your answers the way examiners expect to read them, you're just leaving marks on the table. Every single year, literally every year, the Cambridge Examiner reports highlight the exact same painful mistakes. Students lose marks for missing units, they round their numbers way too early in calculations, they give these vague bullet point explanations instead of actual full scientific reasoning, they mislabel graph axes, they offer super weak practical experiment improvements, and they completely confuse their dependent and independent variables. It's just heartbreaking, because these aren't failures of knowledge, They are failures of exam technique. To fix this instantly, we are going to use a 4-step answer framework. Think of this as your absolute foolproof blueprint for literally any high-mark question. First, you state the core concept. Second, you provide evidence or data directly from the question itself. Third, you apply scientific reasoning to connect the two. And finally, and this is the kicker, you wrap the whole thing in precise examiner wording. This framework instantly upgrades any response from a panicked guess into a rock-solid, structured, mark-winning argument that examiners absolutely love to see. So, the crucial point is, you have to ground everything in the exact definitions the syllabus demands. Let's look at the foundational concept of an electromagnet. According to the source material, an electromagnet is created by passing a current through a coil of wire. Okay, that is step 1. But the crucial modifier, the part that actually secures that extra mark, is stating that the strength of this electromagnet is increased if it has an iron core, which then becomes magnetized when the current is switched on. If you literally memorize this exact phrasing, you are already thinking exactly like an examiner. Now let's apply the scientific reasoning step of our framework to something visual. A really common exam question asks you to compare magnetic fields. The golden rule you absolutely need to pull from the syllabus is that the magnetic field around a solenoid, which, remember, is essentially just a coil of wire acting as a magnet when current flows, is exactly the same as the magnetic field around a standard bar magnet. Recognizing this identical pattern is the hard evidence you need to back up your scientific reasoning when you're asked to draw field lines or predict magnetic behavior in a circuit diagram. In a moment, I'll show you the examiner clue that changes the answer completely, but first, you need the framework that makes that clue obvious. Let's keep building our toolkit so when we actually hit that high-level clue, you'll be fully equipped to handle it like a total pro. We really need to look at another highly tested concept: electromotive force, or EMF. The specific definition you must use is that an EMF is induced in a conductor when there is relative motion between the conductor and a magnetic field. Notice the incredible precision there. It's not just moving a magnet, no, it is relative motion between a conductor and a magnetic field. This precise concept is the foundation for the absolute most challenging questions on electromagnetic induction. If you don't nail this definition right out of the gate, the rest of your answer will completely fall apart. And this brilliantly illustrates the next crucial layer of the syllabus: proportionality. If that conductor is in a complete circuit, the induced EMF actually produces a current. The examiner wording you need right here is a direct proportional statement. The larger the induced EMF, the larger the current that flows. So, if a question asks what happens when you move the magnet faster through the coil, your evidence is the faster relative motion, your concept is the induced EMF, and your examiner wording is explicitly stating that this results in a larger current flowing in the complete circuit. It's a chain reaction. Okay, let's escalate the stakes a bit. You are now looking at a classic, extremely high-pressure, practical investigation challenge straight from the workbook. The question asks, describe at least 2 precautions you took to ensure accurate measurements of the time taken to raise the mass. Practical questions absolutely terrify students because you can't just recite a memorized definition. You have to actually evaluate an experiment. So how do we tackle this without completely losing our nerve? Well, you tackle it by breaking the practical evaluation down into 2 mandatory steps. This is exactly what the mark scheme demands every single time. Step 1. Suggest the specific experiment improvement or precaution. But hold on. Here is where most students stop, and exactly where they lose the mark. You must always include step 2. State the exact effect that specific improvement would have on your data or the accuracy of your measurements. Just stating an improvement in isolation is totally useless if you don't scientifically justify its impact. Think about a really weak practical answer that might just say, I would use a better stopwatch to measure the time. The examiner gives that straight up 0 marks. Why? Because the word better is incredibly vague and it doesn't state the effect at all. Now contrast that with an examiner-approved answer using our framework. I would use a light gate connected to a data logger to measure the time taken. This improvement removes human reaction time error, making the final time data significantly more accurate. Do you see the huge difference there? It gives a specific physical improvement and directly links it to the effect on the accuracy of the data. That right there is a flawless practical evaluation. Let's move to and see how this builds back into our main electromagnetism topic, delivering on that crucial examiner clue I promised earlier. When you get a question about a magnet moving near a wire, the ultimate examiner clue, the real secret to unlocking those top band marks, is this. You must explicitly link the relative motion directly to the size of the induced EMF, and then logically connect that to the resulting current. Examiners report year after year that students mention the motion, but totally forget to mention the EMF, jumping straight to the current. No way, you can't skip steps. You have to show the complete chain of events. Motion induces EMF, and EMF produces current. So you now have the exact framework. You know the precise definitions for electromagnets, solenoids, and induced EMF. You even know exactly how to structure your practical evaluations to guarantee full marks. But here is the critical vulnerability, the elephant in the room. How do you deploy this exact framework perfectly when the exam clock is ticking down, your palms are sweating, and that sheer panic sets in? Because having the perfect knowledge is entirely useless if you just run out of time to write it down. Losing track of time in the exam hall absolutely destroys perfect knowledge. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_GCSE to excel in your Cambridge examinations. We break down these exact examiner strategies so you are never ever caught off guard. Because, listen, your preparation isn't actually finished yet. You have this structural knowledge from this explainer, sure, but the massive unresolved problem is exam timing. If you don't know how to pace these perfect answers, all of this strategy just falls apart. That is exactly why your mandatory next step is our Physics 0625 Timed Answer Writing System Explainer, which you can jump into right now. But before you do, I want you to seriously ask yourself, how many marks have you already lost in past papers simply because you knew the physics, but you just ran out of time to translate it into the language of the examiner?